In the previous video we have seen that under parity transformation the equations of motion of a point particle in the presence of an electric and magnetic field remain invariant if E goes to minus E and B remains invariant. Similarly, under time reversal, the equations of motion remain invariant if E remains unchanged and B goes to minus of B. In this video we will see that under these transformations of electric and magnetic field under time reversal and parity, the field equations, that is the Maxwell's equations, also remain invariant. Now the Maxwell's equations in free space are the following: divergence of E equals rho by epsilon naught, divergence of B equals 0, curl of E equals minus del B over del T, and curl of B equals mu naught current density plus epsilon naught del E over del T. Now under parity, del goes to negative of itself and E also becomes negative. Therefore this quantity, divergence of E, remains invariant. Hence this first equation remains invariant. In the second equation, del again goes to negative of itself and B remains invariant, so we get a negative sign on the left hand side, but on the right hand side we have 0, so this equation also remains invariant. In the third equation, del goes to negative of itself, E remains invariant. E also goes to negative of itself, therefore this curl of E remains invariant. While on the right hand side, B remains invariant and T remains invariant because we are considering the parity transformation, and in parity transformation it's the spatial coordinates which change sign and time remains invariant. Therefore the right hand side of this equation also remains invariant, therefore this equation remains invariant. In the fourth equation, del becomes negative, B remains invariant, therefore on the left hand side we get a negative sign. On the right hand side, J becomes negative because J is charge density times velocity, and velocity becomes negative under parity, therefore J becomes negative, and this E attains a negative sign and time remains unchanged. Therefore on the right hand side also we get a overall negative sign in front of this equation. These two negative signs cancel and this fourth equation also remains invariant. Now if we consider time reversal, then under time reversal this first equation is invariant because under time reversal E is unchanged and del is also unchanged, therefore the left hand side of this equation is unchanged. This equation, left hand side of this equation is unchanged because del remains invariant under time reversal, E also remains invariant. And on the right hand side we have charge density, which is not affected by time reversal, therefore this equation remains invariant under time reversal. Similarly, the second equation is obviously invariant because on the right hand side we have 0, b goes to negative b on the left hand side, but this only gives a negative sign, and since on the right hand side we have 0, this equation remains unchanged. In the third equation, E remains invariant, del remains invariant, therefore the left hand side remains invariant. On the right hand side, b goes to negative of b, but t also becomes negative, so the right hand side also remains unchanged, so this equation also is invariant. In the fourth equation, b becomes negative, therefore on the left hand side we get a negative sign, and on the right hand side j becomes negative because j is simply rho times the velocity, so j goes to negative of itself. E remains invariant, E goes to E, but t changes sign, t becomes minus t, so we get an overall negative sign on the right hand side and overall negative sign on the left hand side, so these two signs cancel each other, and so this equation is also invariant. So Maxwell's equations also are invariant if electric and magnetic field are transformed like these under parity and time reversal.